Right, so we have Albert Jiang now and telling us about not the cynics but the realist guide to AI for maths research. Over to you.
Thanks. Thanks. Hi. So the reason why I'm crossing out cynic is that I was really hesitating between whether I should use cynic or realist, and now I noticed that on the Google slides you have this. You can generate images like from Gemini. So I thought, okay, what does Gemini think? So I asked it to generate me two images, one of a cynic and one of a realist. So I got image of a cynic like this, and the image of a realist like this. So I immediately picked the realist. You know, especially the bananas. Those really did it for me. So it's a really aesthetic choice to name the talk "A Realist Guide to AI for Math Research." Okay, so what do I want to really talk about in this talk? So I want to talk about what is the reality of working on AI for formal maths research today, and what are the different incentives in industry versus academia, and how do they actually influence and shape the work that people do, and how do we align them towards a good direction? And of course, these are really big questions, and I don't intend to. I don't think I can do it in the time of a 45-minute talk to answer all those questions. So I'm just trying to focus on maybe just one direction. And so if there's one slide I can take home, I really hope it's this slide. That is, we're in an evaluation crisis. So for AI for formal math research, so evaluation benchmarks really do not reflect how formal mathematicians think currently. And the worst part is that academia as a whole does not really understand how good or bad the models are for helping their work. And academics also over-index on a few benchmarks and has some sort of existential strat, because to actually make good benchmarks, you need to really think about exactly what you do. And industry cannot really help by fixing all these evaluations for you. I'm going to tell you why that is the case. So a small disclaimer is that when I say industry here, I mean general industry. I'm excluding Google DeepMind here because they're kind of a special case, and as long as Demis has your back, you can kind of do whatever you want, and you have infinite compute resources, etc., etc. Okay. Again. There we go. So to begin, I really want to talk. I want to talk about a bit of my experiences and what sort of makes me qualified to talk about this pretty wide topic of AI for math research, both in academia and in industry. So I was working on AI for math from about 2017 and until about last year. So that was just after Transformers came out, and I started to get interested in using machine learning to do AI for math research, and I really wanted to do it in Isabelle. But at the time, the experience with using Isabelle is that you use it in this Isabelle editor, and there's Isabelle server, but it's kind of hard to communicate with it using Python, which is the main sort of language used for machine learning. And so the first thing I did was to write a Python to Scala to standard ML interface, which is called PISA, and that allows you to for Isabelle to become a real machine learning environment, kind of similar to the environment that you will find in OpenAI Gym. And then I started to work on the auto-formalization of theorems and proofs with language models, because they started to become really powerful tools, and because we have so little data for auto-formalization, they became the natural choice for doing auto-formalizations with. Then I started to, I really like hammers, so I started to integrate and improving hammers with language models as well. So I was doing this until about last year when I graduated from my PhD, and then I started to train language models for a company called Mistral AI from 2023. And very recently I was working on reasoning models called Magistral for Mistral AI. So these are my sort of academic and industry experiences, and so I think currently it's a really exciting time to work on AI for math research. So first of all, why do formal research? Why do I emphasize the word formal here? Because in many ways, formal math is really the ideal playground or the ideal environment for both humans and AI. Because first, you enable like very wide collaboration between agents, whether they're human or artificial, and they ensure correctness. And you actually you get genuinely easier verification than generation. I think previously there's some talk about you know we'd like to think that generally speaking verification is easier than generation, which I don't think is the case, right? Like, because for me when I read a proof, I'm constantly doing when I'm just trying to verify a proof, I cannot just exactly just go by the thought of the proof. I have to construct ideas and concepts in my head, and I need to do like validations and refutations along the way. So I think like in many ways, like maybe verification in general in informal language is not that much easier than generation. But in informal land, you can actually have verification that's way easier than generation. Because, well, first of all, you make generation much harder, but then also verification became such a much easier problem. And formal languages are very, very expressive, so you have a very high upper bound for what sort of things you can say in informal languages. So why now? So first of all, good open source foundation models exist. So before, I'll say about 2023, there's not that many good open source foundation models that you can play with to do AI for math, and to train one from scratch, you would need a lot of resources, and it's kind of prohibitive to what sort of research you can do. But also, formal proof assistants are sort of on the cusp of being accepted by mainstream mathematicians. I see like a lot of mathematicians here, and I think it's really gaining a lot of momentum within the broader mathematical community. And third thing is that there's a lot of excitement around AI for formal math research. So that means you get sufficient funding for doing this kind of research. But for that, you need to tell a slightly different story, which I'll come to later. So what is so many useful? I want to talk about like just the general experience and reality of working in industry, about working on general things about AI for math, maybe not just limited to formal math. So why do so many useful tools get invented in industry? So you have things like Copilot, Moogle, Cloud, OpenAI 03, 04, which are, I think in general, quite useful tools too. Maybe not like useful in every case, but you can definitely think of some cases where they will be useful and make the human work quite a bit easier. So I think the reason behind that is that deep learning and consequently large language models, they're actually incredibly good at generalization. And formal math is taken as a special case of coding. So usually what happens is that these language models or these tools are trained on the entirety of code available on GitHub, and like formal math is in there, and they're actually quite good. Like they're trained on all of these formal math libraries and became really good at formal math. And also they don't really have an out of domain generalization problem because they kind of cover every single distribution on Earth. So they're kind of trained to cover every case. So why do we want to do? Why do people want to do AI for math in industry? So first of all, there's enough compute, although it's never enough. There's always more compute to unlock. There's faster processes for everything. So like an idea from being introduced to getting validated can take sometimes just 1 week, and there's a lot of really fast iterations going on. And I think probably the most important part is the industry. You also get good infrastructure. For example, this is one of the this is taken from our recent work on Magistral. So this is kind of the reinforcement learning training pipeline that we have in Magistral, which looks like it only has 4 parts, but it allows you to have like GPU to GPU communication and doing async updates when some language models are generating, which are infrastructure that do not really exist outside of like proprietary repositories, and you need like maybe 10 really dedicated engineers working for half a year on this to get it to perfection. So I think good infrastructure for like doing AI performance research does not like it's not open source yet. It's unlike the foundation models. Foundation models are open source foundation models are kind of okay now, but the open source infrastructure to perform the AI performance research does not really exist in an open way currently. So then why does industry want to do AI for math at all? For 99% of companies, they wanted to do it either because they want to show off, which I think is the case for OpenAI, or they really want to improve the model's capabilities in other areas where there's actually like a financial incentive to do it. So for example, for coding, for analysis, for planning. So math is done as a sort of whenever you want to propose, I want to do AI for math. It's kind of like, okay, I want to do AI for math. Therefore, it will generalize to other domains like coding, analysis, and planning, where there's money. And maybe there's like 1% of true believers. This is the true path to HI, which I think that there's like maybe just 1% of companies who are actually like that. Okay, so now I want to tell you why I want to argue that industry cannot really fix evaluations for you. So like remember the core of the talk is that we're in an evaluation crisis, and industry will not be able to help you fix everything. So I want to bring a case study here, which is the mini-F2F evaluation benchmark. So this is a really nice benchmark. I started about 4 years ago, and this covers around 500 high school level mathematical competition problems. And these are formalized in 4 different languages. So you have exactly the same problem statements in informal languages, but there you have 4 different like Holite, Ling, ISVA, and MetaMath versions of the formalization. So why do I want to bring this case study up? So this is really by far the most popular benchmark for AI for formal mathematics. Whenever you have a new model for doing some sort of formal mathematics, you usually report on this benchmark. And this is the state of it now. So if you just search mini-F2F on GitHub, this is what you get. You get many different versions, and they're very, very different. The first version is the OpenAI version, which was like when it got started in around 2021. It was very incomplete. So I think Wenda and I took about a weekend to actually add the ISVA formalizations to it. And then almost everyone from the OpenAI math team left, so the repository was just unmaintained at all. And then, so Facebook has a version that adds the natural language versions of the formal statements in it. And then most of the team from that Facebook team also left. So then that repository also becomes unmaintained. So then Kai from the bottom left corner said, okay, the original formalizations was in Link 3, but we really need an update. So he had a Link 4 version of it. And then Harmonic also has a different version, which has like some more cleanings. So the thing I want to say here is that industry industry teams move really quickly, and there's a lot of reorgs happening, and people move around. And these repositories, like evaluation benchmarks, are really, really important. And I think if they're hosted on by a company, then when that team leaves or when that team gets reorged into different teams, then it's very easy. And obviously the case for the most popular benchmark, mini-F2F here, that it becomes unmaintained very often. And I think that's just really bad for having a single standard if you want to measure the performances of all your models. So that's one thing why I think like industry is like it's really hard to maintain a single standard for just even a single benchmark for a long time in industry. And the second reason I want to argue for why industry cannot really fix all the evaluations for you is that results are only as good as the people who are reporting them. So the example here is so Harmonic reported so on this benchmark mini-F2F, Harmonic reported a result of 90%, like solving 90% of questions on mini-F2F, And so this is their announcement. We're excited to announce that we have achieved 90% on mini-F2F, a new state of the art that improves on the previous, on our previous result of 83% last month. And then this is the main figure in their announcement. And so you see there are like 3 results comparing with previous works. So you have the Aristotle by Harmonic, DeepSeek Prover, and Lego Prover. But if you actually squint, like you see that they have different labels. So under the Harmonic result, it says resampled validation set. And for DeepSeek Prover, it's expert iteration on validation set. On Lego Prover, it's Isabelle. So like the first 2 results are in Ling, and third result is in Isabelle. And then you think, okay, what is the resampled validation set? And then you have this like small print that says what is the actual thing that they're reporting. So they have like these points, and I read it and I thought, oh wow, that's really different. And what is the difference? So this is the original mini-F2F split. So there are a total of 488 problems, and you're supposed to have 244 for validation and 244 for test. So when you're doing machine learning, what you're supposed to do is that you're training on the training set, and then you evaluate while you're training, you have different checkpoints, and you evaluate these checkpoints on the validation set, and you pick the best one from the validation set, and then you report the performance on the test set. So that's what you're supposed to do with mini-F2F. So the resampled validation set looks like this. So the original 488 becomes like 392 became training set. So you can train on those, okay? And then only 48 is left for validation, 48 left on test. So the reported 90% is on this like little orange block that's 48 validation problems. And like I don't doubt the result, but the case here is that you can use this 300 like about 400 problems that are sort of basically in the same distribution as your validation and test set. Well, you are not supposed to do that, right? You are supposed to train on like MATLAB and things like that, and only report the test performance. Yes.
Did they do cross-validation where they took different samples?
I don't know. So this is what I got from their website. But I think so. This is so if you look at the figure there, then you're really looking at 3 different results.
Yeah. Sure.
So you know, I don't see the point of the figure if each bar actually represents a different benchmark, right? Why do you put it on the same figure? So I mean I don't doubt the 90% result, but I think this is just like and I think it's probably my guess is that this is like whoever is reporting these results, that's like, okay, maybe we can massage it in a way that's like more appealing and more attractive. I don't doubt the validity of the 90% result on the validation set. But you know, we get like these communications are made like on company websites, and like we see the first sentence and we think, okay, that 90%, that's state of the art. But I think the reality is more complicated than that. So and another example is with OpenAI and Frontier Math. So Frontier Math is a suite of really challenging problems. I think a couple of people here have attested to the like how challenging these problems are. And this is a data set developed by Epoch AI used to measure really the frontier performances of the language models on solving math problems. And OpenAI O3 models scored 25% on this benchmark, which is really incredibly high. But then later it turned out that the work was commissioned by OpenAI, and this was disclosed much later. And in the words of the Epoch AI people, we acknowledge that OpenAI does have access to a large fraction of frontier math problems and solutions, with the exception of unseen by OpenAI Haddock set.
Sorry, might you remind us how these the solutions are evaluated to be correct here in frontier math?
Sorry,
the solutions are scored here. Is the LLM that scores them, or?
No, so it's so the frontier math is I think is developed so that the final answer it can be a really challenging proof, but the final answer is usually a very long integer that you can only derive if you got the correct proof. I think that's the design principle of it. But you see, like OpenAI does have access to a large fraction of the problems and solutions. Although, like, I think the final performance is measured on the handout set that OpenAI does not have access to. But then you also have this problem where OpenAI or a company who's commissioning this work does have access to problems from exactly the same distribution, right? So that can also bias your idea of like what's happening. So like these two examples are really like, I'm not trying to like say, okay, these are like super bad. I mean, these are really misleading results. So it can, if you don't look really, really closely, you can believe something that's not what's happening. But what I'm trying to say is that with these like precedents, it's hard for a company to like to try to put out a benchmark, right? Because people will ask, okay, you commissioned this work. Do you have like unique access to some of the problems? And people will doubt the final result that this company report. So there's no real incentive for a company to put out a public benchmark. They have like fantastic proprietary benchmarks and evaluations for like to evaluate their own models and measure progress. But how do you put this out on the if you put out a public benchmark, that the things become much more chaotic and different, right? So there's no real incentive for a company to do this. So what are the incentives in industry? So like for model builders, for example, Harmonic is a model builder. They build models that can perform these kind of tasks. They really want to beat some benchmarks. So there's some existing benchmark, and they want to beat it. And they want to say, okay, we got the state-of-the-art result, and probably have private proprietary benchmark, but they will definitely not share it. And there are like these evaluation providers, for example, Epoch AI or Scale AI, and they create these benchmarks, but they will hold them private. So for different reasons, sometimes these are held private because they want to test it, and they don't want to contaminate the training data for language models and make the results less credible. So they will definitely be inaccessible. And sometimes they are sold as a service, so like to model builders. For example, this is what Scale does. Scale has like a private benchmark, and they ask all the model builders, hey, do you want to test your model's performance on this benchmark? And we can say, okay, we are like an independent like service provider, and we can we'll have some credibility, and we can help you advertise these results. So these are the different incentives industry, and you can see that to have a reliable public benchmark, you don't get it. Like why would anyone do this? So now let's turn to academic evals. So let's say we forget about industry, right? Let's try to build our own evals. Where are we now? It's evolving really, really slowly, I have to say, for both AI for math and AI for formal math. So if we compare with coding, so in 2021, these are the sort of the state of the art. Everyone uses some kind of evaluation benchmarks for coding and math. So for human eval, this is a coding benchmark. Human writes the natural language specification, and the AI is supposed to write the code and check with some unit tests that the unit tests all pass. And for natural language math, is the MATH math benchmark. So you get a question, you are supposed to give an answer, and then you can check with the ground truth. For formal benchmarks, it's probably Mini F2F, which is kind of the earliest one. And in this case, you get a formal statement, and you're supposed to come up with a proof that can compile. Okay, so what's the situation in 2025? So this is kind of this is SweetBench. So it's a software engineering bench for coding. The idea of this is that you go on GitHub, and you have these PRs and issues, and you have these open issues that's not resolved yet. And you're supposed to take the issue, and you have the entire code base available to you. You give all these, the description of the issue, the entire code base to a language model, and language model will generate a pull request that patches some of the files, sometimes deleting entire files or adding new files, and you can see that it generates PR, and then we'll run the unit tests. Okay, so it can say, okay, before the PR, the first 3 unit tests didn't pass, but after the PR, they all pass. Okay, so this is what coding benchmarks are doing in 2025. And you can see it's fairly advanced, pretty complex and involved. You can use like tools like linter, you do a lot of things with it. And when it comes to math benchmark, it's frontier math. You come up with a question, you get an answer, and you check with the ground truth. With formal math, it's proofnet and Putnam bench, on which you get a formal statement, and you're supposed to come up with a proof that compiles. The problems are harder for frontier math. Frontier math is way harder than math. Proofnet and Putnam bench are way harder than mini app to app. But the big picture, like the idea of how they work, hasn't really changed for 4 years. And we have some nice things, but they're more the exceptions rather than the rule. For example, there's this SorryDB project, which I heard about in the iCERM workshop earlier this year by Lenny. And the idea is you try to find active sorries on GitHub, and you're trying to close them. So this is an ever-evolving database and benchmark, so kind of in the spirit of like the live code benchmark if you're talking about coding benchmarks. And you also have mini context benchmark. So the idea here is that instead of having a static code base and you train on a bit of it and then you evaluate on the rest, you evaluate the performance on the new problems that require new lemmas and definitions. This is closer to the practice of a full mathematician. You're always trying to define new things. You have come up with new definitions, new theorems, and you need to use that context, which your language model has never been trained on. Okay, and so there's a really new work with Thomas, Josh, Jeremy, and Sean that we did recently. This premise selection for Linkhammer that heavily utilizes the mini context benchmark, and so we're trying to evaluate on this benchmark to see like how good is the hammer really for when you're trying to come up with when you're trying to formalize something new, and so just as a small advertisement, there's a Linkhammer now, like a semi-working working Linkhammer, and it's in an experimental state. But I really recommend that you give it a try. So just put this thing in your project TOML file. Do a lig update, import hammer, and then enjoy. Give us feedback. We really want feedback on this, and try to iterate and have a nice working Linkhammer. So one of the things you can do is that you can write a proof of the irrationality of the square root of 2, and the blue bits are the human written parts, and the Linkhammer can complete the purple bits. So this is kind of my long-term secret plan to make link proofs also be as structured as the Isabelle proofs that uses sledgehammer. So you only write half statements, and you are only supposed to write every other line. Okay, so sorry, that's an aside. Okay, so academia doesn't really award making benchmarks, like not as much as other kinds of work, because so first of all, developing evaluation benchmarks for of AI for math is really non-trivial. It requires really deep knowledge of AI, math, and full methods, like all three at once, and it needs a lot of resources and dedication to find really hard and uncontaminated problems. Sometimes you have to just come up with new ones, or like pick ones that are like just from your active research, kind of similar to the process of like how you come up with IMO problems. And it really requires the examination of the academic's own mathematical practice, like how do you actually work? What are the parts that you actually want to make into a benchmark? But it's also like really hard to publish a paper on benchmarking. And the reason is like, it really requires a rare combination of skills that your reviewers most likely will know less than you on this topic. And it's not really like rewarded, and it's not the easiest kind of paper to publish. So what is a mathematician's role in bringing about good proof for full methods currently? So there are like different kinds of attitudes towards or like roles that current mathematicians or full mathematicians take. So the first one is the kind of the user receiver. So the information flow is is unidirectional in the sense that the AI companies put out a new tool, and then the mathematicians or full mathematicians play with it. They might consult, like they're just they're customers shopping for a model. They might consult reviews, but ultimately basically just takes it as is. So I keep thinking of like an iPhone or like a phone reviewer when I think about these kind of roles, like you comparing different phones, but ultimately they're a tool to help you do research. So that's fine. That's like, I guess, like most people when it comes to AI things. But like, do you not really want to be in the room where it happens? Do you not want to influence how these AI tools are made for math, right? So like so that's the one kind of role that current formal mathematicians take. The other role is like the people are taking the role of the free quality assurance engineer. What that means is that there are people who diligently analyzes the flaws of current models, whatever the new ones are coming out, and shares the feedback on Twitter or to AI companies, right? So most likely on Twitter. And 2 months later, a new version comes out, and all those problems are fixed. But you have no idea whether like it was the AI company saw your tweet and then just made some small patch and that solves the problem, or just because like purely because of scale, because like they improved on some other aspects and that solved it. Don't you want to know like how the patch was made, and rinse and repeat and become a free quality assurance engineer for the AI companies, right? So this is like the current roles of like I think a lot of I'm not saying all, but like a lot of mathematicians and formal mathematicians at the moment when it comes to evaluation benchmarks. So I keep thinking about this paper that we did in 2023 with Katie, and I think Mattel also talked about this paper on the first day. So this is about evaluating language models for mathematics through interactions, which I think is like at the time we just didn't really have a good idea about how mathematicians actually interact with language models, how they actually use these chatbots. So I think this is really the first step towards doing it. But when it comes to like as an evaluation benchmark, for this kind of things, we need to do it for every single model, right? So whenever a new model comes out, we need to get in this work is all about volunteers. Mathematicians volunteer their time to try to evaluate how do I interact with this model, and that's a really time-consuming, resource-consuming effort. And you don't really want to do this for every single model that comes out. So I think I think this is really for the first step of understanding how things work in interactive fashion. But going forward, we really need like benchmarks that are more cheaply and easily repeatable. Okay, so how do we fix evals? First, I think academia should really make seriously good benchmarks that actually measure how helpful they are to you. I think academics should think about your own workflow and which part do you actually want the AI to take away, right? So like there's a lot of parts where you enjoy. You're thinking, oh, I'm doing mathematics. I really enjoy this part. You don't want the AI to take that away. So why do you want to make that a benchmark, right? You only make benchmarks for things that you don't want to do, right? You want AIs to take away. And also, I think we really should recognize the importance of realistic, uncontaminated, and cheaply runnable benchmarks. And this is, I think, like from the most senior people down, I think we should really recognize the importance of these things. And then the next step would be to make them standards, such that every single model released that claims some sort of performance on formal math or math has to be measured on these benchmarks. So these are my ideas for like how to fix evals. Obviously, they're not comprehensive, but I think with these like fairly simple and solutions, I think you can align the incentives a little bit, right? So for example, for academia, once you recognize the importance of making these benchmarks, you get more like people will like once everyone recognizes, or like the majority of people recognizes the importance of this, there will be more space for doing papers on making good benchmarks. And because it's a really non-trivial thing, it takes a lot of time to iterate. But I think eventually we'll have some useful and good benchmarks available in academia. And I think it's much more credible if an academic team hosts and much more stable to host an evaluation benchmark. But also, if you do this, you kind of force the hand of industry to also follow your lead. The incentives in industry is mostly beating some benchmarks, and once you make these benchmarks, the standard, they have to try to beat those, and then you should actually try to align the work that people do to hill climb these benchmarks that measure the functions that you actually care about, the roles that AI that you actually care about, that you want the AIs to improve on. So a good example is like finding literature. So it's not really measured in like much of the benchmarks that we have today. But if you're starting on a new topic, you might want to, like, after Google Scholar, after all these searches, you might want to ask a language model, like, okay, what are the relevant literature? And if it's a relatively niche field, it's kind of hard to find everything. And we don't really have a benchmark for that. We don't really have a way of telling how good are each model, how good is each model on this, apart from like really anecdotal evidences, like you keep hearing people like whisper, oh, I heard O3 is really good at this, but I don't think it's like we have a good benchmark that sort of makes the experience shared. So I think these are like really to recognize the importance and to find things to make a serious effort on the evaluation benchmarks would be really ideal for this purpose. But also, it's not just the incentives. I think, as Jeremy said yesterday, this field is really exceptionally kind and exceptionally bright. So I think we have all these incentives, and we have ways to try to align the incentives so that they progress on things that we care about. But it's not just those incentives. I think people do this because they love it. They volunteer to do it, even if it's not directly like helpful for their career. But I think, like, with the right starting point for the incentives and the right micro environments, I think we can make really good evaluation benchmarks and hold all the AI for math research more accountable, more credible, and you get a clearer academia and industry to get a really clearer picture of what is going on and what is the state of the AI for formal math research. So yeah, that's the last slide. That's the end of my talk. Thank you very much.
Questions? Asi?
What do you think of the idea that actually looking at the headline numbers of the benchmark isn't that informative, because you can just kind of keep scaling compute and keep increasing the performance on the benchmark, and that it's more informative to sort of include some measure of compute or cost or something in the information for the model evaluation?
Oh, I mean, I think definitely for open source models, absolutely, because you can measure like how much compute they spend. But for proprietary models, you send your questions to an API and you wait for something between 1 second and like 2 hours for a result. I don't really know how much compute that costs. So I think this will be limited to the open source models. But I think in general it's a good idea to also label like how much resources was used for this particular method to achieve a particular performance. I guess like one way that's sort of a surrogate for resource is like the pricing. Like how much did you pay to call this API? How much did you pay to run this model? But also the pricing can be really volatile. Like O3 prices just dropped by 80% yesterday, so it changes the performance, the ratio quite a bit. But I think in general it's a really good idea to report resources or cost in benchmarks.
Jiang.
And thanks for the really thoughtful presentation, and it's kind of stimulating me to ask a question that you may not be able to answer immediately, but perhaps I want you to think about it and you know, give us a response maybe by the end of the week, and for others as well. What would you recommend as moonshot projects that one should contemplate over the next few years?
Okay, I can think about it and answer by the end of the week. Thanks.
Olivia?
So in the beginning you were dismissive about the motivation for using this for coding, but isn't it the same by Curry Howard? And I mean, there are even a number of projects. For instance, I'm thinking of the Microsoft F-Star project where they're doing proof search using LLMs.
You know, to bring Curry Howard, I think, okay, I feel like it's a bit like too far removed from the way that we actually do research. Like, yeah, you can justify it by Curry Howard, but if you look at the you know, what the coding benchmarks are doing, like taking the active issues and, you know, trying to patch them via PR, it takes some effort to translate that to Curry Howard, right? Like, and to full math research. I think you can argue that, but I think in the being a realist, I think being realistic, I think that's a bit far removed from how we actually practice mathematics and full mathematics. You can do that, but I think it's a bit far removed.
Do you see a clear boundary, or is it more of a spectrum?
Yeah, I guess it's more of a spectrum. If you're looking at the Sweet Bench, the coding benchmarks, some of them are, you know, in JavaScript, like just front end things, but there are also like things that are like in functional languages, sometimes in formal languages, but they're rarer. But there's definitely a spectrum of like how close you are to full math.
I don't think it's a bad motivation for people to work on it.
To work on what, sorry?
I think it's a genuine motivation. It's not a perverse incentive for people to work on it. You suggested in the beginning.
Sorry, to work on what?
You said this was not for the true believers to work on coding.
Oh, no, I mean, what I meant was that like on the true believer side, I was saying that, you know, there are true believers who think that full math is the way to AGI, and it's not dismissive about coding. I mean, coding is it's also an umbrella term that covers a lot of the practices what we do in full math. Right? I was not trying to be dismissive. Sorry, I wasn't clear about that.
I'm sorry about the question. What is contaminated problem?
Ah, right. So, the training materials for large language models contains a lot of things.
Yeah.
And for example, if you post a question on Stack Overflow or Stack Exchange, they might end up in the training materials for that language models. So you are training on test essentially. And I think for frontier math, they're like super paranoid about contaminating the language model training materials. Yeah. They were like only authorized to communicate to each other via Signal. You're not even supposed to use email or text. You might get script and being trained on. So like being uncontaminated means like you make sure that these problems are actually unseen. The solutions to these questions are unseen by the language models before. Yeah, that's what I meant by uncontaminated.
Thank you, because it's just
sorry.
Anything, yeah.
Larry?
Okay, you mentioned one of these benchmarks has only integers for all the solutions, so you arrive at the integer and that shows you solved the problem correctly. So as anyone who marks examinations knows, the route to the solution is the real, where the knowledge is, and if someone made a slip along the way but still found the main elements of the solution, they should get some credit for it. So that kind of approach, it makes the marking easier, but it is also not going to miss things that are like partway there. So I don't approve of that. It doesn't seem very appropriate the way we did it.
Oh, yeah, I mean that's like one, like the frontier. You're talking about the frontier math.
Yeah, I guess that's the one.
Yeah, the frontier. I'm not saying that's the only way to do things.
Yeah.
It's just, you you get other problems if you don't use integers, like or easily checkable answers when you're doing this informal math benchmarks. Like if it's like super complex expression, and the model came up with an equally complex expression, to evaluate the equivalence of two is also a little bit difficult at times.
Indeed, yes. Anyone who has marked an exam is perfectly familiar with this.
Yeah. I'm not saying that's also like I'm not saying that's the only way to do it.
Yeah.
It's what they like. You either do this or you use language model to mark the final answer, which brings other questions, right? But like I think the nice things about the formal stuff is that you ensure the correctness in the end, and perhaps we can develop benchmarks that also measure like, okay, you have these like 5 conjectures that are actually correct, but you just didn't get to the end. I think that's totally possible to do as well.
But remember, AI seems to be much better at classifying than it is at generating.
What do you mean by classifying?
Well, identifying instances of a thing like, the thing that you can give it thousands of pap smears and it identifies a suspect one for the better accuracy than a doctor. It's the kind of thing that AI is already very reliable at. So identifying characteristics that suggest something as being what you're looking for is a thing that AI is more or less trustable at the current time, which is hardly the case when it comes to generation.
Yeah, that's why we need formal verifiers, right?
Yeah.
Wenda?
Yes, kind of a follow-up question to the contamination thing. So from like benchmarks proposed by academia is very likely to be public, and then in this case, how can we avoid the data contamination problem?
I think there are ways to do it, right? So it's a technical problem, but I think there's definitely ways to do it. For example, you can, to convince people that this is a good benchmark, you have a portion of your benchmark being public, and you say, oh yeah, these are public things, and we don't use these in the final grading. And in the final grading, you use a different set of problems, and for example, what was done for the AI-MO competition is that there's always a set of held out private questions, and you can only submit your model via a notebook, and then the notebook was run by the benchmark providers, and then there's no way that a company or like anyone else than the benchmark provider can have access to the final questions. So I think it's a technical problem, and there are solutions to this.
Yeah, good, thanks.
Fenner at the back?
So what's your take?
Go ahead.
Yeah, what's your take on how misformalization should be handled? Because there's a difference between, say, SweBench and math, where the answers are all correct. You know the code can't be unit testing because it's merged. You're fairly confident this person did this computation correctly in the math data set. But in these normal data sets, people have written the statement, and they almost certainly didn't write the proof before they made the benchmark. So they released this benchmark, it has these statements in it, and then maybe some company or some academic group runs their model, and they find a proof that looks too easy, and so the proof is uninteresting, or they find it's false. Yeah. And if this is happening behind closed doors, then what do you do? Or if someone submits a model and it gets like 1 out of 100, and then someone else submits one, so they realize, oh, actually 50% of the remaining ones are misformalized, so that previous benchmark score looked worse than it should have been.
Yeah, I mean that's that's a challenge of making these benchmarks. Mini-Aftermath has so many mistakes that we had to like. I think I fixed 10 myself, but there are a lot of mistakes, and this is what makes benchmarking difficult and really takes a lot of dedicated resources. And I don't have a good solution to that, but I think like one good practice would be to version your benchmark. Whenever you make a major patch, you have a like V2, V3, and then you report the performances along the way. Like have different you have one model, but they have different performances for each version of the benchmark, and you only compare the models horizontally on the same version of the benchmark.
And so if the version has misformalizations, we could still say, yes, it got 50% on this version, but this version is known to they're not really the questions they say they are.
Yeah. I mean, it's not going to be perfect, and eventually you might have some. Well, you can have like some. For example, you formalized the statement to some unsolved question, and then 1 day later, a company or like the group says, "Oh, I have full proof to that." You think, okay, maybe that I formalized the statement wrong, but it's really hard to check beforehand. right? But it's not going to be perfect, but dynamically you can definitely improve it over time, and through version you can have good comparisons between different models.
So do you think people making the benchmark should make snapshots every 6 months or something, or should people just quote like a commit at the version they were using? Which of those is the scalable thing?
I think commit will be like too like incremental. I'll probably have like I'll probably have like for every major version you have a version number, and then you can compare it by commit, but you know it's a bit there's too many versions.
Fenner in the back.
Yeah, thank you. I wanted to ask about values and incentives in this structure. So my guess would be that in the examples that you gave of the harmonic reporting and the frontiers mapping, that like, they knew what they were doing when they were misrepresenting this, right? And I think it comes down to a clash in values between researchers trying to do their thing, and when they're in an industry lab, they're bosses who want the showing off bit that you listed towards the beginning. And if that's the case, right, if they're under this sort of pressure, then improving the benchmarks or standardizing the benchmarks doesn't seem to be much of a solution to that. Do you have any comments on, I mean, what can be done to do this?
I mean, I agree, but I think it, like to solve the problem, like if your manager's manager wants to have better numbers, that's a really hard problem I think. But like if you make the academic benchmarks, or if you make your benchmark in general much harder to cheat on, and make sure that everyone sticks to the same standard, I think the problem is at least a little bit better than before, right? It's something that you can't fix that problem from academia, but you can make it harder for them to do that. You have to keep people honest on that point.
Devdat?
So you mentioned that academics don't have an incentive to create benchmarks, but isn't it a strong incentive that they create a benchmark which will be cited by lots of people?
Yeah, but I would like, from my experience of like working on AI full math research, the easiest things to publish will be to like you have a new method, do a slight tweak on some old method, and then give you like some performance boost. That's really easy to publish. But to publish a benchmark, first it requires much more work. You need to basically eyeball and make sure that everything looks. It takes a lot of effort to actually like examine all the data points and to maintain it afterwards. If you publish a method, you can just here's a method, like go play with it. But if you create a benchmark and you need to maintain it, it takes a lot more effort. And compared to the credits that you get, the citations you get, I would think that it's a bit less than publishing a method. I'm not saying academics are not incentivized to publish on benchmarks at all. It's just less so than a throwaway method that you don't need to care about afterwards.
So you mentioned some motivations for why does industry want to do AI for maths, right? And you mentioned showing up and improving other areas, coding, analysis, and planning. Where does reasoning fit in for you? Is that part of the motivation? Is it
yeah, I mean, reasoning is definitely part of it. So like, we found that if you train a model on math, it generalizes to coding. If you train it on coding, it generalizes to math. Like I think there's some underlying reasoning circuits that controls all this. Reasoning is definitely part of it.
Also in like kind of natural language conversations that you would have with somehow the performance in maybe math problems could improve that, or? So
I think like if you train a model on math and coding questions, I think in general you find the model to be much more working with the model to be much more productive. Like you can do things that are more intelligent than before instead of like that's a general observation. But by that slide I was more meaning like these are the areas where you can make money on. Like these are coding, you can sell that as a product. Analysis, you can sell that as a product. But for math itself, it's really hard to sell it as a product.
Jay, on that front, do you think there's room for development of LLM-based tools which would create kind of super mathematicos, not for pure mathematicians to do their research, but for all the people out there who use maths for doing more applied work in sciences, for example?
I mean, definitely. I think like, mathematicians' role is not just proving theorems, right? a lot of different aspects to it. And I think some models are already helping, like for finding literature, these kind of things they're already quite useful. And to create a, I don't think it will excel on every single aspect, but I think it can definitely be a superhuman tool when it comes to like when you just want to learn about a new area or learn about new language, like natural or formal language. It can be super helpful in those aspects. So I don't know if that answered your question.
Sort of, but I just think about the maths that people do out there in the real world. There's lots of different kinds of maths, and one could envisage too that if people are creating a simulation of the weather or something, they want to know that that simulation has been put together correctly and hasn't got bugs in it.
I see.
And so there's a incentive to help people kind of write the code for that, but write the code for that correctly, and maybe this kind of research and LM help can help those people do those tasks more quickly, more correctly.
Yeah, I can definitely envision that, but I just don't have a very specific answer to that yet.
Further questions? Well, thanks very much, and thanks very much, Albert.